Hey guys, I'm 义和王.
Everyone, I'm 依然写。
Hi everyone, this is Wei Jiechen.
Hey guys, I'm Yi He Wang, so I'm going to discuss 5.1 and 5.2 over this live video. So, to effectively align a Hindi laser with the rail, starting by approximately positioning the laser so that its axis corresponds with rail's axis, then install two arises on the rail, adjusting them to their smallest aperture setting and ensuring they are at the same height as the laser. Then fine-tune the laser's alignment by turning the screw on the laser holder, aiming to direct the beam through both arises. To confirm precise alignment, progressively reposition the arises along the rail. A well-aligned laser will consistently project its beam through both apertures, regardless of their position on the rail. This constant alignment across varying positions confirms that the laser arises and their respective apertures are in harmonious alignment with the rail. To assess the level of table, we fixed a pentaprism on the stage. This stage was set up such that one side of the pentaprism face the laser while the opposite side is oriented towards the table. When we then place a trail filled with water between the pentaprism and table, allowing the laser light to pass through it. Upon activating the laser, the principle is that if the table is perfectly level with respect to gravity, the light reflected from the air table should align precisely with the incoming laser beam. This is because the pentaprism is designed to reflect light at 90-degree angle. However, as observed in this video, the returning light did not pass through the arises located between the laser and the pentaprism, indicating a deviation from the original light path. Therefore, we can conclude that the table is not leveled with gravity. To generate two orthogonal beams using a Q-beam splitter, we firstly securely position the beam splitter on the rail adjacent to this. We placed another rail at right angle, ensuring they were perpendicular. On each rail, we mounted an arises. The next step involved carefully adjusting the beam splitter onto the laser light successfully pass through both arises. Achieving this alignment indicates that we have successfully created two orthogonal beams as the arises on the rail are set at 90-degree angle relative to each other. The pentaprism is highly efficient in directing light precisely by 90 degrees regardless of the angle of the incoming light, with minimum loss in light intensity. This consistency in deviation light, combined with efficiency in preserving light intensity, makes the pentaprism a preferred choice in many optical application. On the other hand, a Q-beam splitter operates differently. It divides the incoming light into two paths. One beam continues straight forward, while the other is deviated, typically at 90-degree angle. However, this process results the reduction in light intensity in both transmitted and reflected beam. We installed a rail on the table parallel to an existing first rail. Leverage the alignment of the table screw holes, which are designed to be parallel. This setup allows us to align a Korean laser to its corresponding rail using the same method previously employed for aligning the Hindi laser. For this, we utilize the arises that we previously used in aligning the first laser, ensuring they were set at the same height, which corresponding with the same height for both rails. Consequently, when the green laser beam passed through these two arises, it indicates that the laser was not only parallel to the first laser but also at the same height. To verify this alignment, we turn on both lasers and place a notebook with parallel lines perpendicular to two rails to observe that the light spot from both lasers fell on the same line on the notebook, confirmed that the lasers were indeed parallel and aligned at the same height. We attached a pentaprism to the second rail, purposely positioned to redirecting the beam at 90-degree angle toward the first rail. On this first rail, we place a Q-beam splitter directly in the path of the light reflected from the pentaprism. This beam splitter was tasked with both splitting the incoming light and redirecting a portion of it by 90 degrees to align with the laser path on the first rail. To fine-tune this setup, we installed arises on the first rail. We then meticulously adjusted the pentaprism beam splitter and the second laser until both beams successfully pass through the irises. The ultimate confirmation of our precise alignment came when we observed a single yellow spot on the wall. This result indicated the successful merging of two parallel beams.
Guys, I'm Yuanxian and I will talk about for our lab for 5.3. On 5.3 we have 3 part. Actually, I think the A, B, C part is actually the same, just change the
不然这视频要
lines,
交啊。
the current or covered.
那咱们周末把视频做了吧。
Because we don't have that, we only have 500 and 700. So you can see the video. We do that on the 500 focal length and 75 focal length. We put the laser on the center of the lens. Then on this way we can find the focal point. That means lens never change when we move the display position. And for section D, we put on the same direction. It's a 375 because we change the lens focus, but because the table maybe it's not for the horizontal, so it's not show.
In part 4, we align the laser beam and microscope along the optical rail. We firstly use the same way as part 1 to align the laser beam with the rail and mark the location of the beam on a paper. Then we set up a microscope on the rail close to the laser and face the object lens to the laser. In this process, we change the object length of different NA number and successfully project the crosshair on the wall. The projector spot through the microscope is not centered with the beam location we marked it earlier, so we need to align the microscope. The microscope mount fixed its translation along X, Y, and Z axis and roll about the X axis. 2 screws adjust the pitch of Y and the yaw of Z. We adjust the overall height of the mount to adjust the microscope to move along the Z-axis and adjust the Z-axis tight screw to adjust the relative position of crosshair and marked point along the Z-axis. At the same time, we rotate the whole mount and adjust the screw that control the tilt of the Y direction to adjust the relative position of the crosshair and marked point along the Y-axis. Finally, crosshair coincides with the marked point. After that, whether we move the microscope along the rail or we insert a lens between the laser and the microscope and move the lens along the rail, the projected spot through the microscope remains stationary on the screen and centered with the crosshair.